leadership.
Baby, we live.
Resilience. These were the driving forces for the American Association for Cancer Research.
Hey guys, tell me if you're in now. Let me know if you're in the stream, baby. We've got 5 people in here so far.
This past year has presented so many unexpected challenges. But thanks to our members, supporters, and the entire
we ain't begun yet. How's everybody doing? Please share the stream wherever you can. We get it live, baby. Hope everybody's well. I'm waiting for your comments to pop up. I can see it here on my phone though. Hey Gav. Hey Marty. Oh yeah, baby. We here, baby.
Scientific minds at the first ever
Love it.
conference on COVID-19 and cancer.
Switch this one up quick. How's everybody doing today? You good?
A special COVID-19 and cancer task force.
See the chat at the side.
Advocate forums to identify barriers and develop solutions to optimize.
I wonder why the chat. Oh, there you go. Now it's popping up. I see you. Some of them have popped up now. Let's go, bingo. Come on, Posey. How's everybody feeling today? Did anyone buy any in the dippity dip? We're just waiting for this to start. Hello, everybody. Oh, I see you, Gav. I see you, Gav. Me too, man. Me too. Hey, brother. How are you, Mark? CJ? Baby. Yeah, baby. I see you, JJ. Dynavop in the house. Hey, guapo, ¿cómo está? Oh, yeah. Oh, yeah. Oh, my goodness. You put the house on bingo. 1K more, baby. Ooh. Yeehaw, cowboy. I see you. I see you. We're just waiting for it to begin, baby. I see you, baby. Show me the moon. Show me the moon. Waiting for this to begin at the moment. Let me see where I can share this. Hope everybody's been good today. See when this is going to start. It's on loop. It's on loopity loop at the moment. Oh, baby. Okay. I'm going to switch onto my phone as well, onto the live stream, so I can see all your chat real time and reply. Bam, bam.
This year, we will achieve even more by advancing
Yeah.
science for the benefit.
Yeah, I bought some more today as well. I got into the little dippity dip. Oh my God. I'm the space cowboy, baby. He said, what's up, cowboys? Hope you're all good today, man. Let's switch this over. Bam, bam. There we go. Now I can see it real time. Oh, we ready? Oh, they're beginning already. They're quick. They're quick, man.
Hello, everyone. I'm Yannick Delpu, and it's my pleasure to welcome you to this Bionano workshop session to discuss what optical mapping can offer for the study and characterization of cancer sample. QR codes will be displayed during this presentation to take you to relevant publications or webinars, so you might want to have your smartphone ready. Among all biological tissues, cancer is probably the most complicated to interrogate. Genome instability constitutes a major challenge for the characterization of such a sample by current technologies. And add to that the high cellular heterogeneity, the presence of many clones bearing different genetic alteration. This explains the limitation of NGS and how it led to a lack of understanding of the role of structural variation in cancer, which remains largely overlooked today. And that is very easy to understand when you take into account that 2/3 of the human genome is repetitive, making it extremely challenging for algorithms to reassemble the reads in these regions. And the consequence is that many structural variants will remain invisible to these technologies. Getting reads of several dozens of kilobases using long-read sequencing is an improvement for sure, but when you deal with heterogeneous samples, the coverage is key. when you want to address highly heterogeneous tumors with a highly clonal population, what's the point of spending tens of thousands of dollars in sequencing if you just get a fraction of the information you seek? The way our technology works isn't based on sequencing and can be compared to karyotyping, but at a much higher resolution. With karyotyping, what you have on the left, chromosomes are stained in a way you can distinguish a pattern of bands that is unique throughout the genome, with a band roughly every 5 megabases or so. And any abnormality in this labeling pattern would indicate the presence of a chromosomal alteration. The same way, with optical genome mapping, a pattern of labels is applied throughout the genome, this time with one label every 5 kb on average, and will be scanned and analyzed automatically by the saphyr system. And similarly to karyotyping, any abnormality in this labeling pattern would indicate the presence of a chromosomal alteration. Here, there is no culturing, no amplification, no denaturation, no fish probe needed. And this is how it works. On the left bar of the screen, you can see that electrophoretic cycles are applied to the DNA that will be linearized and elongated in hundreds of thousands of nanochannels in parallel. And that allows the acquisition of a massive amount of data. And by running the instrument a bit longer, you can increase the yield to coverage levels that are simply out of reach of any long-read sequencing technology. And this you can do at no extra cost. On the right panel, you can see the raw data generated with the DNA counter stain in blue and the green labels as the green dots you can see here. Another major difference with long-read sequencing is the size of the molecule we imaged. They're above 200 kb, so we even have the luxury to disregard any molecule smaller than 150 kb for our analysis. So we combine all you need to address complex cancer samples, long-read information at high coverage, and for a few $100s per sample. The workflow is extremely simple. You extract the DNA using our kits to obtain ultra-high molecular weight DNA. This DNA is labeled with our enzyme called DLE1 and counterstain, and this is where the specific labeling pattern is applied genome-wide. The stained DNA is then simply loaded on the chip where the nanochannels are engraved, and from there, everything is automatic. The DNA molecules are imaged, aligned together based on the labeling pattern to create a consensus map that we call an optical map. We also measure the coverage genome-wide to detect any large gain and losses in the genetic material. And ultimately, the sample map in blue is compared to reference in green. This can be the adjacent tissue, control cell line, or simply a reference like a HG19 or HG38. And it is this step of map comparison that will identify any deviation in the labeling pattern that indicates the presence of a structural variant. This is how we represent the map alignment. We always represent the reference in green and the sample map in blue. Here you can see a deletion and an insertion, and we can detect that by measuring the shrinking or the increasing in the distance between the labels compared to the reference. The same way we can detect a repeat expansion like this. We do not need the repeat unit to be labeled. We can detect duplication where this pattern of label from the reference is found duplicated here and over there. Translocation when your map aligns to two different genomic locations, and inversion. And again, we can detect any large variation in the copy number by looking at the coverage. You can visualize your cancer genome in our software called Access, and we represent the results under the form of a circus plot, but let me actually take you to the live instance of Access. You do have the cytobands on the outside corresponding to each region of each chromosome. The dots are representing structural variants that are identified by this map alignment. The color code corresponds to insertion, deletion, inversion, duplications. Copy numbers are shown here with 2 aneuploidies identified in this sample, and translocations are the pink lines at the center. Here you do have an intrachromosomal translocation. And every time you will click on an event, the map will open to show you the details of these structure variants. So here we do have an insertion of 6 kb that is absent from a control database that is directly embedded into our software and allow you to filter the vast majority of the polymorphic variants you can find in a sample. And these variants overlap with the CLC-A4 gene. And here are shown the different structural variation classes which are detected by optical mapping. So we just saw whole chromosome changes with monosomies and trisomies. Seeing these, whether they are terminal or interstitial. Duplications, for which we also give you the insertion site of the duplicated fragments and its orientation, information that are missing from array approaches. Insertions, inversions, pericentric and paracentric, and of course, no problem to detect balanced or unbalanced events like translocations. And we can detect these events down to 1% allele fraction thanks to our high coverage, and this automatically and genome-wide. We can detect, of course, repeat array expansion and contraction. And while we outperform NGS for the detection of structural variation, there is still some complementarity between the 2 approaches, as we do not provide you ATGNCs because we are not sequencing based. So single nucleotide variants and very small indels of a few base pair will be reported by sequencing. With this performance of optical mapping to detect variants missed by NGS and long-read sequencing in particular can be observed in results from a recent publication from the Human Genome SV Consortium. In a well-characterized cell line, not highly rearranged as a leukemia sample could be, for example, the sequencing-based method based on PacBio HiFi missed about 1/4 of the variants identified by Bionano. And many of these SVs that were missed overlapped with complex regions of the genome that can cause macrodeletion and macroduplication syndromes, for example. The publication did classify some SVs as detected by these sequencing-based methods, but upon further analysis, however, most of these variants were in fact identified by optical mapping, but simply classified differently. And overall, less than 2% of the large variants detected by PacBio were actually missed by optical mapping. So we provide the entire workflow for the genome analysis of a cancer sample that includes this saphyr genome imager, which will scan the DNA, the chip on which the nanochannels are engraved, the chemistry to extract and label the DNA, and of course the software, the Access software I just showed you, and that is free and that you can download directly from our website. We also provide datasets if you want to play with. But given its unique capabilities, optical mapping is playing a central role in generating results that redefine our understanding of cancer in fundamental and translational research, whether it is to study key mechanisms of carcinogenesis, to characterize cancer models, or to identify new biomarkers. And this opens new avenues for clinical applications, for the identification of actionable events, and also for the modernization of current diagnostic methods. So let's dive into what we can offer for the elucidation of fundamental questions in cancer research before moving to our value proposition in translational research and precision medicine. The major cellular pathways are known to be altered in cancer, and their understanding is necessary to identify new biomarkers and develop new drugs for personalized medicine or patient monitoring. DNA methylation is one of them and undergoes tremendous changes during carcinogenesis that entirely redesigns the gene expression profile in cancer cells. And recent work from the Tel Aviv University described a method to interrogate the methylome by differentially labeling CPGs on top of the genome-wide labeling pattern applied by the DLE enzyme that we use for SV detection. And the bottom panel describes the methylation status at the single molecule level of the TP53 region, which is and its neighboring enhancers. And this exciting work has potential applications, whether it is to identify new epigenetic changes and new patterns at low allele frequency in cancer for biomarker discovery, for example, to monitor the efficacy of demethylating drugs that are commonly used in leukemia treatment, and also to develop new compounds directly targeting DNA methylation. DNA replication is also a major target for a new generation of drugs in personalized medicines. For example, being able to monitor replication for progression allows to understand the replication timing in genomes, identify fragile sites, but also assess the efficacy of drugs targeting DNA replication and DNA repair. And this can be done by incorporating fluorescent nucleotide in live cells to label replicating DNA on top of the DLE1 labeling pattern that we apply on the genome, and this to map replication fork progression genome-wide. And here, this has been used to measure the replication timing on chromosome 20, as you can see on this figure. But fundamental science is mostly about laying the foundations, the first stones in our understanding of completely uncharted territories. And extrachromosomal DNA illustrates this perfectly. It's an obscure DNA structure displaying a massive oncogene amplification, but its structure, its effect on gene regulation, and its role in cancer in general is completely unknown. And NGS alone cannot extrapolate any structure because the reads are too short, and the optical maps can be used to scaffold these reads and make sense of this NGS data. Optical mapping and the computational analysis of whole genome sequencing were used in this study in combination to demonstrate the structure and make sense of circular ecDNA sequence for the first time. Beyond these applications to study the basic mechanisms in carcinogenesis, a profound understanding of the genomic rearrangements occurring in cancer cells, whether they are study models or patient biopsies, is paramount to improve diagnostic methods, developing new drugs, and improve patient care. And Bionano excels in this domain. And let me focus now on the detection and the resolution of structural variation in cancer and how patients can benefit from it. Many cancer study models are established and characterized and associated with specific genetic defects that help to understand the developments and evolution of this cancer. But because of the limitation of NGS and cytogenetic approaches on tumor tissues, it is clear today that a lot of genetic alteration remain to be discovered, and that our understanding of these models is by far incomplete, with the certainty to identify new biomarkers or therapeutic targets. So in an effort to better characterize uveal melanoma models, the group of David Jeancien at the Curie Institute in Paris used high-C RNA sequencing and optical mapping to identify structural variation leading to fusion genes. And over 1,000 translocations were predicted by high-C data in the two models they used, MP41 and MP46. But only 50 could be cross-referenced with their whole genome sequencing data, and none could be validated down the road, illustrating the issue of false positive calling and the burden of data creation when working from sequencing data. The RNA sequencing approach is pretty heavy. It's identified over 300 fusions using a combination of 5 algorithms and extensive data creation. and only those called by at least 2 algorithms and in 2 independent replicates were considered solid. 14 were kept for validation, all of them found by optical genome mapping, without the need of a complex bioinformatic pipeline here. And they could be further characterized. I think this example really illustrates the simplicity of optical mapping and how we can tackle the identification of fusions from the DNA while providing more information than RNA sequencing. So here, optical mapping detected a tandem duplication at this locus. You have this sequence here in the reference that actually aligns in the sample map over here, but also over there. This leading to a specific fusion between the ACAT10 gene fusing with the MPK gene over there. This was independently identified by optical mapping from the DNA, confirmed the fusion detected by RNA sequencing. But on top of the fusion detection, optical mapping provided the mechanism leading to this event, which is a tremendously important information. So the take-home message here is that you can identify any fusion in a genome without information needed about the fusion partner, and you can interrogate any region, such as IGH, which is notoriously difficult to deal with by RNA sequencing, and this even if your event is present at low allele fraction, because we provide the coverage to do so. But now I would like to switch gear and look at more complex variants. As I mentioned earlier, our conception of the role and nature of structural variation is largely biased due to the technical limitation of NGS technologies. Beyond simple variants like deletion, duplication, translocation, inversions, complex structural variation like chromothripsis, chromoplexy, or templated insertion chains, TIC, can cause multiple DNA junction in distinct topologies. And by sequencing thousands of cancer genomes, new complex SV patterns have been identified, but resolving their exact structure is not always possible from NGS data. You can see here a structure called Pyrgo. Pyrgo means tower in Greek, and it corresponds to a low junction copy number hotspots. It has been identified specifically in patients with ovarian cancer. You have at the bottom evidence from the NGS data of duplication, but the structure of the event cannot be deducted. And this nested structure, you can see here, was resolved thanks to optical genome mapping. One allele is actually bearing all the alteration in the background of a normal allele with a copy number of 5. Analyzing these patterns of duplication with optical mapping is essential because it reports not only on the contiguity of the loci, but also the order of the fragments. So by combining optical mapping and NGS, you can reconstruct extremely complex events. And it is important as these new SV classes can cluster tumors and identify subgroups of patients associated with a DNA repair defect and poor prognosis. And this, of course, paves the way to improvement in patient management. I just mentioned TIC, so templated insertion chains. It is a complex SV class that happens to be associated with a specific signature in hepatocellular carcinoma. You can trace back this signature to patients that develop this liver cancer due to an infection by hepatitis B virus that integrates near a cyclin gene. And this causes a complete deregulation of the cell cycle and replication stress. But resolving TIC from NGS data alone isn't possible because the reads are too short. All you can do is make a hypothesis with 2 different models here, whether it is a chromosome 3 segment from here inserted into a chromosome 1, or a chromosome 1 segment inserted into a chromosome 3. And because optical mapping can completely reconstruct the region with single molecules spanning hundreds of kb, you can unambiguously resolve this event and see here that it is here in the sample map, a piece of chromosome 1 here that inserts in the context of a chromosome 3, validating the second possibility. So identifying simple and complex structural variation is always a challenge with NGS, as we just saw, but the determination of a complex structural signature for patient stratification takes it to another level. And in the same cohorts, the automatically generated Bionano results were sufficient to cluster patients based on the presence of replication stress due to the deregulation of the cell cycle following HPV infection. And these patients harbored a lot more chromosomal instability, and you can see at the center the tremendous amounts of interchromosomal translocation in addition to tandem duplication and insertion that are reported here, slightly differently from the circus plot that we generate. And this cluster is different from the patient without this HPV insertion, where these patients show way less chromosomal instability. And this has exciting potential in terms of patient stratification and identification of subgroups that can correspond to a particular, that can respond, to a particular therapy like PARP inhibitors. And again, this doesn't require a complex bioinformatic pipeline. The circus plots that are automatically generated allow you to cluster these patients. The same way in head and neck cancer, HPV insertion can cause extensive chromosomal rearrangement as well. And the circus plot can cluster patients into two groups. The patient with an episomal form, so not integrated, that will display minimal level of chromosomal instability, from those with an integrated form that will harbor a tremendous amount of recombination and translocation, as you can see on these circus plots. And from this structural signature obtained from our map alignments, Dr. James Broach reconstituted the complex events triggered by HPV insertion represented on these cartoons. You have here in one sample this HPV insertion that will trigger a duplication with HPV at the junction between the duplicated fragments. In this sample, it will trigger a triplication of this fragment over there, but it can also lead to more complex rearrangement with here a translocation between chromosome 11 and 8 with HPV at the fusion between these two chromosomes. And the most extensive rearrangement here with a focal amplification of that region mediated by HPV, followed by a duplication of this neighboring fragment. So the take-home message here is that having single molecules of hundreds of kbs to entirely reconstitute highly rearranged loci opens the possibility completely out of reach of long-read sequencing, whether it is to make sense of NGS data, to find new SVs or biomarkers, or to assemble complex structural signature. But how does it apply to the field of precision medicine? This is what we will discuss in the last part of this workshop. And on that note, I would like to hand it over to Dr. Darren Finlay. Dr. Finlay is a research associate professor and director of tumor analysis at Southern Burnham Presbyterian in La Jolla, California. He is a cell biologist with a broad interest in oncology and drug sensitivities, and has been stratifying responsive patient-derived cancers based on genomic features, including structural variants using the saphyr system. So Dr. Finlay, the floor is yours.
That introduction. As Yannick said, I'm Dr. Darren Finlay, and I'm from Sanford Burnham Prebys. And my talk today is going to be talking about the use of optical genome mapping to uncover novel structural variants in leukemias, and how we can associate these structural variants with drug sensitivities. These are my disclosures. So just a brief introduction to acute myeloid leukemia, which is the main focus of my presentation today. Leukemias in general are actually increasing in prevalence over the last 20 years, which is probably due to an aging population. And acute myeloid leukemia is not a very prevalent disease. There's only about 21 to 22,000 new cases a year in the United States. However, it is a major killer. More than 50% of those people will die. So some patients do respond to standard chemotherapy, which is cytarabine, a DNA analog, and also a alkylating agent, which is usually a member of the rubicins, daunorubicin. I explicitly mention that because I'm going to show an example of that later. Some patients do respond to the standard of care, somewhere 30 to 35%. However, they almost all relapse. And the only cure for acute myeloid leukemia is bone marrow transplantation where possible. So there's a major unmet need to identify new or extant drugs, but also to identify patient populations that will be responsive to these drugs. So for our preliminary studies, we have analyzed 9 samples. We've actually analyzed more than 20 now, but our initial studies is just going to be focusing on these 9. This is the basic clinical information. What I really want to highlight is that through traditional cytogenetics, either karyotyping or FISH, we know of 6 of these structural variants that are already present. That is the deletion of chromosome 7 in this sample, BCR-ABL translocation in these 2 samples. This sample also has a deletion of the Y chromosome. This sample has a rearrangement of the CBFP gene on chromosome 16, which is a known event in AML. Finally, this one has a deletion in chromosome 6. What I really also want to point out is that 4 of these samples are considered normal or negative by traditional cytogenetic analysis. Traditional analysis will find nothing wrong with these samples, even though they're obviously not normal because they do have leukemia. So it was of interest to us to see what could we find using optical genome mapping. So this here on the left-hand side is the concordance between the traditional karyotyping FISH cytogenetics and what was found by optical genome mapping. And all of the events I described in the previous slide were detected. That is the deletion of chromosome 7, BCR-ABL translocation from chromosome 9 to 22 in these 2 samples, deletion of the Y chromosome, the inversion event on chromosome 16, and this deletion on chromosome 6. On the right-hand side here, what you can see is that there are many, many more structural variants that were also detected, even in the samples that were considered normal by traditional cytogenetics. So we usually range from around 40 up to as many as 80. And all of these structural variants are filtered against a database of healthy volunteers. So none of these structural variants have ever been found in a healthy individual. These are all almost certainly involved in the pathogenesis of the disease itself. And the color scheme, again, is going to be consistent throughout. We find mostly deletions and insertions, but we do find duplications, inversions, and some translocations. This is just one example from one of our relapse samples. So we knew when this patient first presented that they had this deletion on chromosome 7. You can see it here in the gene track. We can also see many more deletions across chromosome 7, which could well be involved in the disease progression. But we also detected 2 translocations that were not found on an initial presentation. That is this chromosome 2 to 11 translocation and 5 to 11. So this suggests that traditional cytogenetics is not sensitive enough to detect these, or that these translocations were present in a very low clonal population that is now taken over, suggesting that optical genome mapping could also be used for progression, to track progression of the disease. And just one last example of a circus plot. This is one of our samples that was considered normal or negative by traditional cytogenetics. And we don't see any translocations here. What we do see are all the dots around here, the circus plot, represent structural variants. We found 13 insertions, 37 deletions, an inversion, and 2 duplications. So a lot more structural variants detected using optical genome mapping. And indeed, one insertion event that we detected in this sample, and insertion events, I'm led to believe, are extremely hard to detect using traditional next-generation sequencing methods. But here we find a 32 kilobase pair insertion in the middle of a lysine methyltransferase 2A gene. This gene has been implicated in AML before. So a sample that was considered normal by cytogenetics, we find this potentially pathogenic insertion in a known disease-causing gene. So We do have 100% concordance, but this table here is supposed to show that we've detected a lot more structural variants, and we have manually curated what we have found to try and associate them with genes that may be involved in cancer progression. So you can scan along the gene list here and find your favorite gene. The real point of this is to show that we detect all the different kinds of structural variants, and the color scheme I'm using throughout is going to be consistent. What we find is we mostly detect deletions and insertions, but we also find duplications, inversions, translocations. And just the two examples I'm going to show up the top here, BCR ABL, it's a translocation. We find it in 2 of our samples, but it's always the same thing. For example, we always, BCR ABL is always a translocation. This here in CDK11A, it's always a deletion. The 2 samples have it as a deletion. Similar here, it's always the same. So these are probably just not random events that we're detecting. These are probably true causative events that are involved in the pathogenesis of disease. So that is one of our data sets, structural variants, but what we're also interested in is differential chemical sensitivity. So all the samples that we take, we screen them against 120 FDA-approved oncology drugs, and we decide their viability. So this here shows the differential chemosensitivity. That is, we're only showing the drugs that actually show sensitivities that are different in at least one of our samples. I'm just going to highlight some of the drugs that I'm going to use as examples later on. The BCL family inhibitors, which are now used in leukemia. Venetoclax is approved. Topoisomerase inhibitors, such as doxorubicin and valrubicin, which again, as I said, are frontline agents in leukemia. Another example I'm going to use is dasatinib, or targeted kinase inhibitors, which are not used right now in leukemia, but are used in other blood cancers. So this volcano plot here is the integration of these 2 diverse data sets. Every spot in this volcano plot represents a structural variant that occurs in at least 2 of our samples that is associated with a change in drug viability. That is, in blue, structural variants that are associated with resistance to the drugs in question, and in red, structural variants that are associated with sensitivity to the drugs in question. So as I said, every spot here represents one of those associations. I've just highlighted a few here that I'm going to give as specific examples in the next few slides. But what this shows is that there's a wealth of information you can get from these 2 diverse data sets once they're overlapped. This is just another way of showing our top associations. In this waterfall plot here, we see the top 5 structural variant drug associations that sensitize to the drugs. On the other side, the top 5 structural variants that are associated with resistance. And as you can see is that BCR-ABL translocations are involved in sensitization to some drugs, but resistance to others. So we chose this BCR-ABL fusion as our proof of concept. And these are just the 2 circus plots here at the bottom, showing this translocation from chromosome 22 to 9 in both samples. And if you remember from the start, one of the samples also had a deletion of the Y chromosome, and that's marked here with the arrow. And the lower panel here is just the genome level map. So we can see the optical genome map in blue. It's tracking along chromosome 9 perfectly until it gets to this breakpoint in the middle of the ABL gene. And then it maps back up again on chromosome 22 in the middle of BCR. And what we find is these 2 samples, when compared to our other 7, are much more sensitive to the targeted kinase inhibitors, dasatinib, nilotinib, or bosutinib. This is not a surprise, because these agents are known to target ABL and similar kinases. And in fact, imatinib, or Gvec, is actually designed as a selective inhibitor of BCR-ABL fusion. So this is not a surprise, but this is our proof of concept. So what this shows us is that we can, by using an unbiased manner, we can detect structural variants, we can detect drug sensitivities, we can overlay these, and we can find associations that we would expect. But what of associations that we would not expect? Thankfully, in this sample, the BCR-ABL, the 2 samples that have BCR-ABL translocation are more resistant to BCL2 family inhibitors. In this case, an experimental agent, ABT737. But as I said, other agents, such as venetoclax, which target the same proteins, are now used for leukemia patients. So patients that do have BCR-ABL translocations are less likely to respond to this drug based on our findings. And similarly, with the proteasome inhibitor carfilzomib, it's not effective against the samples with the BCR-ABL translocation, but is effective against the wild-type samples. Another example is a gene called CDK11A. It's also known as CDC2L2 tumor suppressor. And just one of the gene maps we're showing here shows a rather large deletion right across the body of the CDK11A gene. So this could indeed be causative or involved in the pathogenesis of this disease for these patients. Interestingly, the two samples that do have this deletion in the CDK11 gene are more sensitive to the rubicin family of drugs, doxorubicin, daunorubicin, valrubicin. These are all structural analogs. And as I said at the start, daunorubicin is a frontline agent. So although CDK11 may be pathogenic for this disease, there is a good prognosis or potential prognostic value for patients that receive daunorubicin. And just again, an unbiased association, another indirect DNA damaging agent, tenipicide, shows a similar profile. And then one final example is a deletion in a gene I had never heard of before, but again, it shows the value of this sort of unbiased analysis and detection. So the deletion in a gene called KIF26B, this is a kinesin, which is involved in trafficking of cargoes along microtubules. So it was gratifying to see that the two samples that had a deletion in this kinesin were resistant to a microtubule targeting agent, paclitaxel. They're also resistant to mitomycin C and triethylene melamine. And I'm not really going to discuss it today, but I'm just going to allude to it. We also study other diseases other than leukemia. And in 3 of our childhood brain cancers, we have also found a deletion in KIF26B or its homologue KIF26A. So in summary, optical genome mapping shows the 100% concordance with traditional cytogenetic analysis. And as I hope I've shown, we don't just find those 6 major translocations and deletions that we knew were there, we also find many, many more. And using these integrative analyses, we can associate these novel structural variants with chemical sensitivities and drug resistance to clinically relevant agents. And just by way to whet your appetite, we don't just do this in leukemia, we're also analyzing glioblastomas, childhood ependymomas, and primary CNS lymphomas. And as I mentioned previously, all 3 of the ependymomas we've screened have shown deletions in kinesin family members. And with that, I would just like to thank the Flore Lab at Sanford Burnham Prebys, also Junyin and Rabbi Murad from the Sanford Burnham Prebys Bioinformatics Core, our collaborators Jim Mason and Carol Borian, who provide us with the leukemia samples from Scripps MD Anderson, and of course all the team at Bionano Genomics, who were involved with analyzing the first 6 of our samples. Thank you.
Thank you, Dr. Finlay. And these are great results and really illustrate how patients will benefit from optical mapping, whether it is to identify classical rearrangement informative for a diagnostic procedure, but to profile tumors in precision medicine, thanks to our ability to detect structural signature and actionable fusion, and to also complement and modernize the current standards of care to improve patient management with a more streamlined workflow that you can see on this slide. We're seeing tremendous adoption all over the world, and numerous studies are now evaluating optical mapping against the standard of care for cancer patients. I would finish this workshop with the results from 3 users that nicely illustrate how optical mapping can modernize cytogenetics, identify clinically significant variants missed by a standard of care, and push the boundaries of precision medicine. The first study is a multicentric study led by Bryn Levy from Columbia University and James Broach from Penn State University. It is a landmark study where optical mapping was compared against the standard of care in 100 AML cases previously characterized by karyotyping, FISH, and chromosomal microarray. And not only Bionano identified all the clinically relevant variants, SVs and CNVs, reported by these standard of care, but it also identified additional variants in 11% of the cases that have been missed by the routine methods. So it showed the ability to identify balance events like balance translocation that you can see here from the karyotype between chromosome 10 and 13 and 8 and 21 that would be represented by these lines over there and between these chromosomes here and there. But also, it showed the potential to identify cryptic events that were missed by karyotyping in this example, where a translocation H21 was identified, as you can see here, but a translocation between chromosome 4 and 5 was missed and was detected by optical mapping with a deletion of the 5q terminal region that can have a significant impact to stratify patient into in terms of risk assessments. And since optical mapping is a new technology, the authors modeled the optical mapping nomenclature on the array nomenclature described by ISCN 2016. But since microarray technology cannot detect balanced rearrangement, they have proposed a unique nomenclature using this ISCN logic that you can see over there. The conclusion of their study is that besides identifying all clinically relevant SVs and CNVs reported by the combination of the technologies that constitute their standard of care, and reporting on additional SVs missed by routine methods, optical mapping also refined the genomic structure reported by traditional cytogenetics, and identify additional clinically relevant variants in about 24% of the cases. And most importantly, in 6% of the cases of patients presenting a normal karyotype, optical mapping directly identified additional clinically relevant variants and or CNVs, including fusion events. So this has a clear potential to improve the patient management in the future. And optical mapping identifies way more events than classical cytogenetics because we have a better resolution and we are not targeted approach like FISH, but the amount of data generated isn't an impediment to an easy characterization of cancer sample. Some structural variants, translocations, for example, are considered hallmark for risk stratification of leukemia patients. And in a few clicks, you can highlight events reported in international guidelines published, for example, by WHO or NCCN. To do this, you can simply create a panel, a virtual panel like you have on this screen. We call it a bed file that will extract from the genome-wide interrogation of the genome all the events impacting the loci of interest that you listed in this file. And of course, this panel can be customized at will and combined to one another. So in this AML panel, you do have here reported 5q deletion. You can have a 7q deletion. You have any event impacting the KMT2A gene, any event impacting the translocation H21, leading to a RUNX1, RUNX1T1 fusion, and also inversion on the chromosome 16. You can create this panel for any cancer, any pathology that you wish. We can make one for CLL, where besides being able to assess the complexity of the karyotype directly from the circus plot, you can also directly pinpoint any event impacting the genes like Notch1, BCL2, that is evaluated for patients to orient the patient towards specific treatments, and also a deletion in the 17p, including the TP53 gene over there. But actually, let me show you how it works live on a sample. This is an ALL sample where we loaded such bed file that follows some guidelines and include gene lists reporting in those guidelines. And you can see that comparatively to this previous flows I showed you, you do have an extra circle over there with blue bands, and those bands are actually the genes that are documented in this bed file. If I zoom in, one is RUNX1 over there. This is BCR, but you can add any gene you want. And so in this circles plot are reported the variants that have been identified in this sample and screened against our control database to remove the polymorphic variants that are found in the normal population. And I simply have to go to this bed file and decide to show only the SVs and CNVs that overlap with this gene list. And in just a few clicks and just a few seconds, I will have just the filtering of this genome-wide information that will allow me to focus only on the variants that are overlapping with genes that are reported to be clinically significant in this cancer. If I click on this one, this is a deletion of the EBF1 gene. So it's very easy, and we can see that the identification of hallmark variants is easy with the Access software, and while a lot of new clinically relevant variants are still identified, and that will completely unnoticed with the standard of care because they were not expected and because FISH or panel sequencing are targeted approaches. And this leads me to the second study from Children's Hospital Los Angeles, where Dr. Gordon Araka reported the identification of variants missed by standard methods and not identified by their custom gene panel, since it was not expected in this type of leukemia. And this illustrates the importance of genome-wide unbiased structural variation detection as provided by saphyr. Dr. Raka does genetic testing of pediatric leukemia at CHLA and routinely performs a FISH, karyotyping, chromosomal microarray, and their OncoKids NGS panel. And interestingly, they routinely observe about 15% of B-ALL and 5% of AML cases where the key genetic driver remains unknown. And 8 of these negative samples were run on optical mapping to determine if it can detect clinically significant genetic drivers missed by their comprehensive molecular evaluation done on their routine workflow. And 2 cases really stand out in terms of discovery that I would like to develop a little bit. This sample is from a patient that had a poor response to treatments and developed a residual disease requiring more aggressive treatments down the road. A translocation 2.5 was identified by karyotyping, but at the time of diagnostics, they did not really understand the significance of such rearrangement. Optical mapping found that the same alteration, but could locate the breakpoint at a much higher resolution. And an interesting gene was found at the breakpoint of this translocation, the PDGFR beta. This event was later, of course, confirmed by FISH and RNA sequencing. And PDGFR beta is associated with what they call feel-like ALL, which is linked to high-risk ALL and associated to a better response to tyrosine kinase inhibitors. So this patient could have been treated accordingly with imatinib or tisagenib if this translocation was better characterized at the time of diagnostic. And the interesting question is, why was it missed in the first place? Well, first of all, because the fusion of the PDGFR beta with this gene SPTBN1 has never been described in BALL before, but only in very few cases of another hematological malignancy. And hence, it wasn't expected in this type of ALL, and this is why it was absent from their OncoKit panel. This second patient was also identified as a standard risk patient and had an even worse response to treatment than the first one and had to be involved in a CAR-T trial to get into remission and however relapsed shortly after that. Karyotyping seemed perfectly normal and CMA didn't report abnormalities. And to their surprise, when they ran optical mapping, it reported numerous rearrangements they were completely unaware of. And this is most likely due to the fact that leukemia cells can sometimes not grow or grow poorly depending on the cultural condition. And this really illustrates the potential of working from uncultured cells with optical mapping. And here, in this pretty complex circus plot, a 3-way rearrangement between chromosome 1, 6, and 12, leading to a fusion between MEF2D and FOXG2 was identified. MEF2D fusions define a specific subtype of BALL, and FOXG2 is a very rare partner described only once, explaining why it was not part of their NGS panel and why it was missed in their initial comprehensive testing. And this fusion was confirmed by RNA-seq. And the clinical significance is that MEF2D fusions are associated with high-risk disease and very poor outcome, explaining the aggressive cancer in this patient. And that information would have been crucial to risk stratify this patient. So it's striking to see the discoveries made in cancer sample for which the standard of care is already focusing on the identification of structural variants. And that really highlights the importance of applying optical mapping in solid tumors, cancer types where classical cytogenetics is not applied as it is in leukemia, and where structural variations tends to be largely overlooked. And Dr. Ravinda Kohli from Augusta University evaluated optical mapping against a SNP array that is part of their routine workflow in brain tumors. Among different samples included in the pilot study, they observed 100% concordance with the SNP array, like you can see on this sample. So at the bottom, you do have the OncoScan results showing all the large gains and losses identified in this sample. And you can see how they perfectly matched the results of the Bionano whole genome CNV plot that is reported on the top panel. But many other variants, structural variants, copy number variants, many translocations, completely unsuspected, were found, and many of them impacted well-known oncogenes or tumor suppressor genes like BRAF, EGFR, or CDKN2A. And this is really illustrating the importance of looking at those structural variation and having this genome-wide analysis done at high coverage thanks to optical mapping. So their conclusion is perfectly concordant with the two previous studies we saw, with a clear potential of optical mapping to identify new, unique genetic abnormalities, new fusions without any information on the genes impacted or the fusion partner needed. Think about NTRK fusions, for which dozens of fusion partners have been described. You clearly do not want to use 30 different fish probes here. And also to the potential to improve SV characterization in those complex karyotypes that have been shown by Dr. Raka. So the results are so conclusive that this study is on the path of a laboratory developed test for solid tumor at Augusta University. So as a conclusion, optical mapping is a long-range technology that overcomes NGS limitation and access regions of the genome inaccessible even to long-read sequencing, because it's due to highly repetitive sequence, because these regions are flanked by segmental duplications, or because they are composed of high GC contents. Its coverage, up to 1600x coverage, can interrogate heterogeneous tissues and allow the detection of structural variants down to 1% allele fraction, automatically, genome-wide, and for just a few $100s per sample. Unlike RNA sequencing, it can detect fusions automatically and provide additional information on the mechanism leading to the fusion events, even if this event is falling into complex regions, such as the IGH locus that is notoriously difficult to deal with by RNA sequencing. And this without any information on the fusion partner. And of course, it will also detect any SV or CNV affecting the regulatory sequences. From the different evaluation, we saw that optical genome mapping can identify classical rearrangements, informative for patient diagnostic on risk stratification. It shows outstanding concordance with the standard of care, but at a much higher resolution. It can identify actionable, druggable events without a priori information often missed by conventional workflows, and it can also reconstruct complex structural signatures automatically without the need of a complex bioinformatic pipeline to run. So I really hope all these applications convince you to try our technology. You just have to flash this QR code to access our website and get in touch with our sales representative. And we will be happy to answer any question you have in the chat or by directly getting in touch with us. On these notes, I will thank you for your attention. I would like to thank again Dr. Finlay for being with us today and presenting such outstanding results. So until next time, goodbye.
Until next time, goodbye. Is it over?
Oh,
it's
American
over.
Association for Cancer.
It's over, baby. What do you guys think? What do you guys think, man? Oh, juicy. Kablow! Love it, Cowboys. I've been watching you for a few weeks and I truly appreciate what you do. When I take Bingo along to the promised land, I'm going to throw you some bones. Oh, baby, I love the bones, man. Woo! Juicy. I eat the marrow. I'll eat the marrow. This is huge, bro. Loved it. Is it? What's the stock price doing at the moment? Is this presentation completely over? What time is it? It's nearly 7. Yeah, it's probably over. I'll check what the Bingo price is saying as well in a minute. Oh, what are you guys saying here? Oh my God, we got a lot of messages, baby. We got Jamie R saying access regions of the genome inaccessible. Yeah, when I saw that in the summary, I was like, oh, even to long read sequencing. You know, that's a serious little phrase there, baby. Serious. They need to take note. I wonder if Simon is watching this. Are you in here, Simon? Say hello, Simon, baby. The QR scan straight to the sales, baby. When is the next ones? Which next ones are you talking about? Talking about the prototype or the next throughput one? The higher throughput machine, Sapphire, is that what you're talking about? For the stock price to match the potential. Oh yeah, me too, baby. Me too. I actually picked up some shares today. I managed to pick up just a few. And I'm literally huge, baby. Eric said huge. Waiting for the perfect time for leaps. Oh, me too. Let's go. Let's go, baby. Thank you very much, man. Appreciate you guys. Thank you very much. He said £6.59. Oh, they on 6.59, 6.60. Are they? Oh. Patience. I see where you wrote pay in there. Patience. Oh, baby. What did he just say? I just wanted to order a pizza. Oh, bro. What toppings did you get? Oh my days. This is jokes. Remember, guys, we do have another presentation later tonight that we're going to be streaming. What time is it going to be? UK time. I think it will be 9:15. Let me check my diary. I gotta check my diary, baby. So make sure you don't miss. Yeah, 9:15 p.m. UK time. It's the hot topics one, so don't miss out on that one too. I think they're gonna talk about sequencing first, and then later on down the line within the hot topics, it's an ACMG live stream. So later on down the line, we're gonna have a segment as well. Someone is using the Sapphire machine there. Oh baby. Oh yeah. I see you guys. Thank you guys, man. Thank you for all attending. And don't forget to check in with the next one later on tonight. So that one's going to be good. Go get some food. Go get hydrated. And then we'll be ready. We'll be rocking and rolling, baby. Thank you very much, guys, for attending. And I'll see you later on. Oh, juicy, Robert. Below 50 cents, you know. How did you find it back then? What a gem. What a gem. Thank you, guys. Kenny said, price is crumbling. Come to daddy. Come to daddy-o. Baby. Thank you, guys. Catch you guys later. See you later, footballs. Yeah, make sure to set the reminder. Where should I share it? I'm going to share it in a bit, actually. See if I can reshare. Let me get the link up. I'll get the link for you now. April 14th, ACMG. Get that link. Tell me if you guys could access the link here. I don't know if it's going to block me from posting my own link, but if not, I'll put it on Twitter. You're welcome, brother. I appreciate you so much, man. Thank you so much for always putting great content on StockTwits. That's why I follow you there, baby. You got the greatest. You and Cisco Trader, you always have gems, bro. Gems. The next one's tonight at 9:15 p.m. UK time. I'm not sure what that is in American time. Where are you based, Kenny? You can find the link in the saloon. In the salon or the saloon. In the salon, baby. Oh, I love it, guys, man. All right, guys, I'm going to end it. I'm going to get some something to eat and something to drink. So get hydrated, baby. And we're ready for tonight. Ready to rock and roll. But yeah, thank you so much for attending, guys. And I'm going to catch you later tonight. I hope you guys all find the link. I'll post it up in Twitter in a bit. Oh, baby. Oh, yeah, Kenny's in the UK. Yeah, bro. Love it, man. Yeah, so 9:15 p.m. tonight. ACMG Hot Topics. Hot and fresh out the kitchen, baby. All right, guys. Peace out, man. From the cowboy. Mr. Invest a lot. Over and out, baby. We got to end the stream, man. Okay.